base conversion. So let's say we have base 8 and base 2, these two numbers, and both have decimal value of 9. So they have different radix, but they have equivalent value of 9. So that then we say they are equal, and let's convert 41 to binary now for the conversion. So what we are doing is dividing, because we want a binary number, we divide it by 2, and we got 20 here, and there is a remainder here, and quotient is here 20, and we divide the 20 with 2, and we have 10, and we don't have remainder now, and that's how we continue until the end, and we have the remainders here, and we put 1 for remainder and 0 for 0 remainder, and we have these coefficients, and we put them in order like this from A0 to A5, and that's the binary equivalent of this 41 in decimal. You can write it like this too. 41 divide by 2, and you got 20, you have 1 remainder, and divide by 2 again, 10, and remainder here, and continue. And then these numbers, you start from the bottom to up, and that's your answer. And let's make another conversion from decimal 153 to octal, base 8. So what we are doing now, to convert it to base 8, we divide it by 8, and we got 19 here, and the remainder is 1. We divide 19 by 8, and we have 2, and the remainder is 3. And we divide 2 by 8, and we got 0, and the remainder is 2. So we put them in order from bottom to top, 231. That's the octal version of the decimal 153. And that's what we did, what I showed you. And let's convert the 214 decimal to hexadecimal now. So we divide by 16, and we got 13 and 6 remainder. And divide 13 by 16, you got 0, and you got 13 remainder. And we say 13 is D in hexadecimal, so we put them in order from bottom to top, and we got this number in hexadecimal. Want to convert fractions, how we are doing it is that. So this time we multiply it by 2 times this number. We got 1 integer and 0.3750 is the fraction part again. Then we get that fraction part here, and we multiply it by 2, and we got 0 integer because it's 0.75, and the fraction part is here, and we multiply this fraction by 2 again, and we got 1 integer, and because it's 1.5, the result, 1 integer here, and 0.5 fraction is here, and we multiply 0.5 again by 2, and we got 1 integer plus 0 here, and we take the coefficients from here now, a minus 1, a minus 2, a minus 3, a minus 4 here, and what we are doing is we put them in order that I already told you how to put them in order after the, like in the fraction part here, and that's the binary number of a fraction, decimal fraction. Octal and hexadecimal numbers, we are using them because they support shorter patterns of binary numbers, 1s, 0s. So since octal 8 is 2 to the 3 and 16 is 2 to the 4, and we divide every 3 digits, we group them, or every 4 binary digits for hexadecimal and write them. And let me show you here. So we have that number in octal, and that's the octal. That's what they are in. This is binary, and we want it in base 8 octal. So this is, we group them every 3 digits, we group them, and we got the value of them, and we put them in order like this, and we have base 8 version of this binary number. So we group them in group of 3 digits. So now if you want to do it, you can do it. Did I press it? No. So you can see the decimal, binary, octal, and hexadecimal numbers. So same numbers with different bases here. And for the hexadecimal, we group them in 4. It's like this. We have this binary number. We want it in hexadecimal, base 16. So we group them 4 groups, and that's what we get. So that's the hexadecimal version of it. This is 2, this is 15, which is F, and this is A, B. So A is 10, B is 11, so this is 11. So that's how you write it. Conversion from, I hope I didn't go over this. Conversion from octal or hexadecimal to binary. No, I didn't teach you in online these topics, right? Do you remember I was teaching this in online course?
No.
Oh, okay. So conversion from octal or hexadecimal to binary. Now we are doing vice versa. So this is the octal number. We open it and we put 3 digits binary for each number in octal, and we write it like this. So this is 4, this is 2, this is 1, and 3, 7, 6. So we got the binary version of it. So we want this hexadecimal in binary form. So we create a binary 4-digit number for each digit here in hexadecimal, and that's how you write it. So I think this was this week's topic, complements of numbers, or maybe still from last week. I don't know, we will see. So complements are used in digital computers to simplify the subtraction. So we want computers to addition instead of subtraction because it's difficult. So by using addition instead of subtraction, it leads to simpler and less expensive circuits to implement for the operations. So we are using basically one equipment, one component to do all the operations like addition and subtraction. We are using only one component for that. So we have 2 types of complements for each base R system. One of them is the radix complement, the other one is the diminished radix complement. First one is R's complement, the second one is R-1's complement. So the R's complement this is the binary. For binary, r's complement is 2's complement and 1's complement. For decimal number, 10's complement and 9's complement, which is radix and diminished radix complement. Okay. So to calculate it, we have a number n in base r, and it has n digits. So we want r minus 1 complement of n. So it's diminished radix complement, and we define it as r to the n minus 1 minus n, the number itself. So for decimal numbers, r equals 10. So r minus 1, 9. So the 9th complement of n is 10 to the n minus 1 minus n. So if you want to use 9th complement of this decimal number, 546,700, so we get all digits 999999 minus the number itself, and we have this, so this is 9th complement. So for this number we have 0 at the beginning, so if we want 1 2 3 4 5 6 digits, if the number has, so this is also the digit. It depends on what they tell you, what they ask you. So if there is 0 here, you will make 9 minus 0, 2, and you will have this number, 9's complement, diminished radix complement of this decimal number. So let's go to the diminished radix complement for binary number. So we have r2, r minus 1 is 1. So the first 1's complement of n is 2 to the n minus 1 minus n. For this one, 9's complement, okay, same thing, same as the other one. So for example, if we have 4 digits, we have 2 to the 4, so this is the number, and 2 to the 4 minus 1 is this. So what we are doing is this number, which is here, minus n, and we get this. So no, we don't get this. So from here we get this, and we are gonna subtract number n from this. So that means we are what we are doing is binary numbers obtained by subtracting each digit from 1. So if we have, let me see this one, okay. So if we subtract binary digits from 1, so we can have 1 minus 0 is 1, or 1 minus 1 is 0. So that means we just change the bits from 0 to 1 or 1 to 0. So the 1's complement of binary number is formed by changing 1's to 0, 0's to 1. And 1's complement of this number will be this number. What we did is 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0. We just convert them. We just switch 1 to 0, 0 to 1. And this is the same way. You can understand it. So the radix complement is, if we have n digit number n in base r, so r to the n minus n is the radix complement of a number. So what is the difference? We don't have minus 1 here. In diminished radix complement, we had minus 1 after that. So basically it is plus 1 to diminished radix complement. So this is diminished radix complement. Plus 1 is radix complement here. So tens complement of decimal is this. Is what we are doing is we find the nines complement here plus 1, and we have this number which is radix complement, tens complement. And the twos complement of binary, we have this. And what was the ones complement? Diminished radix complement is this. We just convert the number from 0 to 1, 1 to 0, and we had this number. And if we plus 1, we will have radix complement, which is twos complement. And the tens complement of this number is this. Why? Because you subtract every number from 9 and plus 1, you have this. The twos complement of this number is this. Why? We convert the numbers from 0 to 1 for each digit, and we edit 1, and we will have this number. You can calculate it by yourself, and this is the same. You can try it. And subtraction with complements. So we are using complements to do the subtraction for computers, and subtraction will turn into addition. So what we learned in elementary school, we were doing subtraction, and we used the borrow concept. We borrow a number from the more significant digit to make subtraction. So when we borrow 1 from a higher significant position, and the minimum and digit is smaller than the subtrahend digit. So this method is good for people, for us, because we are using paper and pencil, but computers cannot do that. So their system is different. The way they are working is different. So they are using complements to make this process efficient. So let's do the subtraction of two n-digit unsigned numbers, n minus n, in base R now. What we are doing is we have m. What we are doing is m minus n. This is n-digit, means the number of digits here. It's not the number. It should be like n-digit. Okay, so instead of m minus n, instead of subtraction, what we are doing is m plus r's complement of n. So we are taking the r's complement, radix complement of the second number, the subtrahend, and we just add them to each other. So we are not doing subtraction. This is addition now. So if m is larger than n, the sum will produce an nth carry, which is r to the n, and which can be discarded. We will discard it, and what is left will be the result of m minus n. If m is smaller than n, the sum does not produce an nth carry. That's how we will understand it, and the result will be r to the n minus m. So this will be the result, and which is the radix complement of n minus m. Whatever we found from there, we will convert it. We will take the complement of it. So to obtain answer in a familiar form, take the radix complement of the sum and place a negative sign in front of the number. So that's how we are doing it. So let's say we have this number m. So what we are trying to do is m minus n. So m is this, n is this. So since m has 5 digits here, 1, 2, 3, 4, 5, and n has 4 digits. What we are doing, both number must have the same number of digits. So we write n as 0, 3, 2, 5, 0. So both of them are 5 digits now. Now we need to get the radix complement, tens complement, because we are doing decimal number. Tens complement of n. And it is, so taking the tens complement of n produce a 9 in the most significant position. We produce 9 here in the most significant position when we calculate the tens complement. And m is larger than n, so the nth carry, we have an nth carry here. See, we have extra digit here. So that means our result is positive, and we will discard this nth carry. So we will have this number, and we will say the result of this subtraction is this number, which is positive. Now let's see vice versa. So we have this 4-digit number minus that 5-digit number, and this time we are gonna get the tens complement of this number. This is n now. So as you can see, we got the tens complement of this, and we put the number here. After the addition, our sum is this number. Do we have nth carry, extra digit here? No. So that means our number is negative, and we put negative sign here, minus, and we will take tens complement of this number and minus tens complement of this number, which is this, will be our answer. Is it true? Yes. This minus this number because this is a small number and this is larger number, and the result is negative, which is correct. So if you want to do it with the binary, so from here, I guess, not from here, maybe after the other page, this week's topic, I'm starting what I teach, what I'm supposed to teach in this week. Until here, it was last week's topic. That's what I believe. And so we have two binary numbers now, and we want subtraction again by using 2's complements. So x minus y, y minus x. We write x here, and we got 2's complement of y, which is we convert 1 to 0, 0 to 1, and we add 1, and we have this number. You already know how to calculate it now. And the result is this. Do we have extra digit? Yes, we will. That means we have positive number, and we discard this, and the remaining part of this number is our answer. So that's positive, this number. And if we want to do vice versa, y minus x, and we got y here, and 2's complement of x, which is this. We convert this number 0 to 1, 1 to 0, and plus 1, and we have this number. And after addition, we have this result. Do we have nth carry? Do we have, there is no nth carry, there is no extra digit here. That means it's negative, and we will take 2's complements of this, radix complement of this, and minus radix complement of this number will be this number, and that's our result. And let's do it with the by using 1's complements. So the same binary numbers we are using, and we are doing x minus y, y minus x here again. And x minus y is, we get x here, and we are gonna get the ones complement of y, which is just switching the numbers 0 to 1, 1 to 0. And after the addition, we will have this number, and it has end carry again, as you can see here. And the end carry means our number is positive, and we will discard it. But because we are using ones complement, we will add 1 here, and we will get this number. Because we were doing it with 2's complement, which is radix complement. Now we are using diminished radix complement, and we discard the end carry and we add 1, and this is our result. And positive this number. So for y minus x, as you can see here, we use y, and for x, we are switching the numbers 0 to 1, 1 to 0, and we put it here. After the addition, we have this number without any end carry. There is no end carry here, and that means our number is negative. And we are taking the ones complement this time, because we came here with ones complement, diminished radix complement, and now we are going back to diminished radix complement again, and we are taking the diminished radix complement, which is ones complement of this number, and minus 0, 0, 1, 0, 0, 0, 1. So here now, the signed binary numbers. For the signed binary numbers, we know that positive integers include 0 can be represented as unsigned numbers. That's how we are using them. But if we want, we can put negative integers. We need for negative integers, we need a notation, and we put minus at the left side of the number. And we can use minus or plus sign if we want to show positive numbers, if we want. But for negative number, we have to put minus. And because of hardware limitation, computers must represent everything with binary digits. Because what we are doing is, we said that computers are using binary numbers. So that's how they work. And that's how they work. So we cannot send to the switches and the transistors plus or minus sign. We have to send 1 or 0. So we have to represent minus or plus sign with the binary numbers. So what we are doing here, we represent the sign with a bit placed in the leftmost position of the number. And so the method is, the sign bit is 0 for positive number and 1 for negative numbers this time. And in the table, you can see that if you go look at that side, so what is that? For 7, we need 3 digits, right? 1, 1, 1. So 3-digit number is enough. But this last one, the leftmost one, is 0 is our sign bit. If it is 0, it is positive. And if you go here, 1, 1, 1, and we have 1 at the beginning, that means it is negative 7. And we can have this. And these numbers, let's take them here. And if we want 2's complement of these numbers, we just, what we are doing, for example, for 7 plus 7, 2's complement is this number. You can calculate it and see the difference. And 6 complement is this number. And this is, we are going to use these numbers, this method, for the arithmetic operations. I'll show you in a little bit. So arithmetic addition, let's do the arithmetic addition. The addition of 2 signed binary numbers with negative numbers represented in signed 2's complement form, obtained from the addition of the 2 numbers, including their signed bits. So a carry out of the sign bit position is discarded also. Let's say we have plus 6 and plus 13 and a positive 6. So 0, 1, 1, that's 2 plus 4, which is 6. This is 13, you can calculate it. And after this addition, we have this number, which is 0, positive, and this number is 19. So if we want 6 and negative 13, this addition, for negative 13 we are taking the 2's complement, and this is 2's complement of 13 in 1, 2, 3, 4, 5, 6, 7, 8 digits. If we are using 8 digits, this is the 2's complement of 13. So 2's complement of this number is here. If we have a carry out of the sign bit, we will discard it. Don't forget that. And from minus 6, this is the 2's complement, radix complement of 6, positive 6. And we add them and we have this number. And you can check if they are, if you can do it or not. They are easy. So for the subtraction, what we are going to do is we have minus 6 minus 13. So two negative numbers and subtraction. So in normal way, when we calculate it, it's plus 7, positive 7. So in binary with 8 bits, we are doing 8 bits operation. So this is minus 6 and this is minus 13, negative 13 and negative 6, and subtraction. So what we are doing, we have to change the subtraction to addition by taking 2's complement of this number. This is m, this is n. So 2's complement of this number will be this. And after the addition, we have this number here. And removing the end carry, that's the result of our addition, which is the answer to this subtraction. We have extra digit here, and the remaining part is our plus 7. So the meaning of this, the computers need only one common hardware circuit to handle both types of arithmetic. So what we are doing is we are using only addition for computers. So it makes the subtraction easy for computers. So they don't need extra components for that.